the title of when Margaret asked me to talk, taking care of your own shit, immediately resonated with me in my work. And that's really what I'm going to be talking to you mostly about today. Just as a quick background, I'm a landscape architect. I'm also a human geographer, and part of what I do is think about the political ecology of soil, mainly in Latin America. So today, in talking about taking care of your own shit, it seemed like a good opportunity to talk about some of my research around Mexico City, which is on the world's largest wastewater agriculture system, where people are sort of literally taking care of their own shit, or trying to. And I'll get into the kind of complexities of what that actually means, hopefully, today. So can everyone see my screen here? Yeah, okay. Well, yeah, so the title is The Right to the Sewage. And the sewage that I'm talking about, again, is this massive wastewater agriculture system outside of Mexico City. But before I begin to describe that, I want to sort of start with this film clip from El Buzo. It's a short film by the young filmmaker Esteban Arangois. And in this film, we're really first confronted by a kind of strange scene, which is, I think, almost scaleless until we see this sort of diver appear from the top of the image, getting lowered slowly into what appears to be a solid surface in the midst of this kind of, massive concrete infrastructure. And, at least to me, nothing really makes sense about what we're seeing until the camera moves to the diver's point of view, where we can see that this is not a solid surface at all, but a surface that consists of thousands of pieces of trash. And what we're seeing here is, in fact, a part of Mexico's deep drainage system called the Drenaje Profundo, which collects all of Mexico City's sewage and stormwater runoff into a single massive pipe. And as the diver sort of enters this surface of trash, for a brief moment, we're able to see that it's actually a liquid surface floating lightly on top of a deep reservoir of wastewater before all light is immediately extinguished by the thickness and total opacity of this water. There's really like no perceptible gradient of lightness to darkness that would even give us an indication that the diver is moving deeper. The darkness of the water is sort of total. And later in the film, the diver will actually tell us that he sort of feels like he's in outer space on some kind of cosmic voyage. And as we stare into the blackness of this film, the impulse, at least for me, is to sort of search for some sign of the water's materiality, some kind of flowing movement that would give us a sense of its viscosity, a brief ray of light that might reveal the smallest current coming from the diver's movements. But there's really just nothing at all. It's totally black. And for me, what I sort of love most about this film is that it really stages what is the central paradox of something that I kind of want to refer to in this talk as wastewater urbanism, which is essentially the search for the materiality of the waste stream. And in this waste stream, we're confronted with an opaque material whose properties are sort of enigmatic and mysterious, also for many people, overwhelmingly disgusting. And our intuition is to sort of totally externalize this waste, to sort of flush and forget, not to take care of our own shit. But in the film, we find ourselves in the diving helmet of a man, Julio Cesar Su Camara, who really cannot, of course, forget at all. For the diver, there's no possibility of this, but the only possibility is to search through that material depth of the wastewater. And I wanted to start the talk here because this is sort of precisely the perspective that we're going to need to take today if we're sort of going to properly understand what I want to suggest in the term wastewater urbanism. But before we get deeper into the Mexican context of this, I want to take a step back and also just quickly consider the global context that it emerges from, not not everyone is familiar with wastewater agriculture, let alone wastewater urbanism. And so to do this, I want to understand some numbers really quickly. For me, at least, I have a daughter. In the time it's going to take her to grow up, she's quite young. Urban water demand is going to increase by 80%. And this number is, of course, fueled by expectations of how many more people will be living in cities by 2050. And the logic here is pretty simple. So when population increases, water demand also increases. The consequences of this prediction for global water scarcity are important to understand. So in this map, we see global water scarcity through time, rather than sort of averaging everything over the course of a year. This map goes month by month and shows us which areas in the world experience severe water scarcity for at least 1 month out of the year. And what this map shows is that an astonishing 2/3 of everyone on Earth, or about 4 billion people, live under conditions of severe water scarcity for at least 1 month out of the year. And of course, these 2 in every 3 people on Earth are not distributed evenly. Nearly half of the people live in India and China. So that's, of course, like 4 billion people. That's a lot of people with very little water for at least 1 month a year. But, an equally astonishing 500 million people in the world face severe water scarcity all year round. So it's an image of water scarcity today, but this is going to get worse, as we just learned, when wastewater when urban water demand increases by 80% by 2050. So about 28% of the world's largest cities are moving towards a sort of quote unquote day zero, where they completely run out of water. This includes, of course, the famous case of Cape Town, South Africa, which has the sort of dubious honor of being the first city to reach day zero, or almost. But on the same trajectory are cities like Sao Paulo, Istanbul, Buenos Aires, Karachi, Nairobi, and of course, the subject that I'm going to speak most about today, which is Mexico City. And we should also remember that climate change will increase the intensity and frequency of floods and droughts, making this dwindling water supply less predictable. So as the engineer and environmental scientist Pi Dreschel recently pointed out to me, wastewater is the only water source that grows in quantity with increasing water demands. So at the same time, water scarcity is increasing, so is the availability of wastewater, such that wastewater production globally is expected to increase 51% by 2050. And, so I think for us, the obvious question becomes, how could this increasing supply of wastewater be used to meet the increasing water demand? That's the sort of question we're left with. But today, as I think everyone in this panel knows, over 80% of the world's wastewater is released to the environment without treatment. So basically, the default global strategy for wastewater, as we know, it causes algal blooms, aquatic dead zones, and contamination. We are not taking care of our own shit. This is what I meant earlier when I said sort of flush and forget. It's the current wastewater paradigm that we all live in. And of course, this 80% figure is a sort of average. So in reality, we know that the geography of this 80% is highly diverse. High-income countries, about 70% is treated, 30% is released. Low-income countries, about 8% of the wastewater is treated. So there are enormous regional differences in treatment, but basically it still all goes to the ocean. So then just following through on this very simple question, if we're sending our wastewater, treated or untreated, straight to the ocean, how might that wastewater be reused to combat water scarcity? Well, one idea is to use the wastewater for agriculture, since we all know farming uses the vast majority of all freshwater resources on Earth. Agriculture, not cities, represent the biggest user of water. So the question becomes, what if we turn the competition for water between agricultural producers and urban areas into cooperation? What would it look like, for example, to create a system of exchange where agricultural producers send fresh water to urban areas and urban areas then return the same amount or maybe even more water to agricultural areas in the form of wastewater, right? So the farmers are sort of competing with cities for water. But of course, what's paradoxical about this competition is that they're also completely dependent on cities. Farmers want to sell their crops to these same cities, which of course have to have water to be in a position to buy agricultural goods. And in the cities, in turn want low cost, high quality food grown locally. So this idea of swapping water for wastewater is essentially a way of formalizing an interdependency that already exists. And creating a kind of a circular economy that sustains its own resource requirements. So it sounds like a great idea. And what I want to do is sort of, put a pin in that and call this the sort of, utopian promise of wastewater agriculture. And I want you to sort of keep this in mind through the rest of the talk, because I think from here on out, what I want to do is actually sort of discuss the reality of this dream in Mexico City in all of its sort of complexity as people actually try to do this. But before I do that, I want to address one last simple question that many of you might sort of already be having about this global picture, which is how much does this actually already happen today? So if we think about like this black screen that you're seeing here, as like all of the available agricultural land on Earth, so an estimated 5 billion hectares of agricultural land, then only about 200,000 hectares is irrigated with treated wastewater in a planned system. And if we consider the agricultural area that's informally irrigated with untreated, raw, or diluted urban wastewater, then we're looking at an area of roughly 36 million hectares. So, something like the size of Switzerland or something like that, right? So there's informal wastewater reuse going on around the world, but really little to no formal reuse. And this informal system is what we find in Mexico. So that was the sort of global picture of wastewater agriculture, or a kind of portrait in numbers. But this is where we get to what it actually looks like on the ground in the world's largest and longest running informal wastewater agriculture system in the world, in a place called the Mezquital Valley, just north of Mexico City. And this is essentially the world's best case study for the long-term viability of wastewater agriculture. And here we find what I think is a very surprising conflict. So this conflict gets to the heart of the question of how to think about the circular economy we just outlined. It gets to the heart of what we think about when we try to imagine what it would mean to take care of our own shit. So we just, kind of went over a very straightforward argument for how wastewater can begin to close the gap in global water scarcity through a system that leverages the mutual interdependence of the urban-rural food waste system. But in all these abstract numbers, something was sort of left out of the conversation, which is what actually mediates the conversion of wastewater into food. And of course, as everyone here will know, that's the soil. And soil, it turns out, is really at the center of this conflict that you see here in this image of several thousand very angry farmers marching in the Mezquital Valley. Behind them are these digesters, anaerobic digesters for an enormous treatment plant, which was built outside of Mexico City. And it was essentially sort of built to move this area from the informal category of wastewater agriculture into the formal category, moving from the big square to the small square in the last slide. And they were trying to do this through the construction of what is now the largest wastewater treatment plant in Latin America. It may be close to the largest treatment plant in the world, just outside of Mexico City. These farmers are not happy about it. So if we remember our film El Buzo, this is the water that the diver was swimming in. It all arrives here to this brand new treatment plant opened in 2017, which essentially promises to send these farmers treated water from their farm fields, or for treated water for their farm fields, right? So of course the question for us is, what's wrong with that? That sounds great. How could the farmers possibly be upset about this, right? In a country with very little wastewater infrastructure and serious health and sanitation challenges, how is it possible that a wastewater treatment plant has provoked protests and acts of civil disobedience? So in this image, the farmers actually occupied the wastewater treatment plant, preventing its employees from entering or exiting. And the basic idea of this treatment plant, which is actually not still fully online and only began partial operations in 2017, is to begin treating sewage before it arrives to these farmers' fields, removing both the pathogens and the free fertilizer that are inextricable from one another in the waste stream. So, right, the farmers call this plan a theft of organic matter. By removing the organic matter from the wastewater, the government transforms the very soil under the farmers' feet, making it, in their eyes, less fertile, less alive, less profitable, kind of like a land grab from inside the soil itself. So what's become controversial in the Mezquital Valley is that the essential mediator that was sort of missing in our earlier portrait of the utopian promise of wastewater agriculture, that is the soil, is really doing a lot of work in this system. And the controversy here, we might say, is over what kind of soil to live in, where the farmers see the organic matter in the soil as the labor of 4 or even 5 generations, built up slowly over a century through careful cultivation. The government really only sees the outline of pathogens in proximity to unprotected citizens. For the farmers, this labor of generations was immense, almost, I think, to me, unimaginable. In these images, you can see the essential aridity of the Mezquital Valley as the context to this labor over the last century. And the farmers of the Mezquital used the wastewater from Mexico City to transform this dry landscape of mesquite and maguey or agave into Mexico's largest and one of Mexico's largest and most productive agricultural areas, growing products like corn, alfalfa, cilantro, squash, zucchini, and the marigold flowers that you see on the Day of the Dead celebrations in Mexico City. And just to sort of orient you on a map, this transfer of water took place at an immense scale over a long period of time. As the basin of Mexico's population transformed from just over 500,000 people at the beginning of the century to more than 22 million people today, the quantity of wastewater that the valley receives also rose proportionally. And what started as a kind of lazy surface stream is now really a torrent of wastewater that delivers 60 cubic meters of water or wastewater per second through a 6-meter diameter pipe. And there are now actually 2 pipes. A new one just opened up last year. So the Mezquital Valley is now both the largest and longest running wastewater agriculture system in the world, and it's become what we might call Mexico City's reciprocal landscape. If the hydrological basin of Mexico has become a desiccated, fully urbanized, post-lacustrine soil in which water scarcity now affects over 10 million people on a daily basis, its wastewater has created a roughly proportional reciprocal landscape of 90,000 hectares of verdant, green agricultural land in the Mezquital Valley, where water is abundant. Its subsurface aquifers are actually overflowing. These aquifers were filled entirely by wastewater. Essentially the water you drink now is wastewater that's like 10 years old. And there's even sort of new springs that have emerged lower down in the valley where the kind of groundwater intersects with the valley, creating new springs in what was formerly only sort of dryland scrub. And so for the farmers in the Mezquital Valley, this wastewater represents an enormous free subsidy in the nitrogen, the phosphorus, and potassium that the sewage contains, making it possible to farm without the need to buy any additional fertilizer in a valley whose soil can support 3 crops a year. For these farmers, the wastewater is a kind of miracle. It makes life possible in the Mezquital. And although there are health risks associated with the wastewater, Poverty, of course, as we all know, also has its own health risks. But what are these risks exactly, right? Well, flooding the valley with this massive quantity of untreated wastewater from Mexico City results in soils that accumulate heavy metals, pathogens, parasites, surfactants, like you see here, antibiotics and pharmaceuticals carried in this wastewater. And there are other strange soil and water properties that can be found here. So many of the irrigation canals in the Mezquital would not pass the federal drug test for cocaine, and also contain some of the highest surface water concentrations of the drug metformin, which is the most commonly prescribed diabetes drug in Mexico City and also in the world. Metformin is the most abundant by weight of all pharmaceutically active compounds in the wastewater of the Mezquital. And this finding is really a kind of chemical confirmation of a crisis in Mexico that's well known to public health workers. So of the 36 member countries in the OECD, Mexico has the highest incidence of both diabetes and obesity. So if we remember our benchmark year of 2050 from before, when urban water demand will have increased 80%, well, by 2050, the lifetime risk of diabetes for all Mexicans will be somewhere between 1 in 3 people and 1 in 2 people. In other words, the soil in the Mezquital Valley and its vast enteric network of pipes, reservoirs, and canals has come to reflect in precise and intimate chemical detail the bodies of 20 million people and the urban fabric of their lives in a seemingly endless expanse of Mexico City. At the same time, the city you see in this image is rapidly running out of water to send to the Mezquital. And today, groundwater extraction is causing what we should kind of call, large-scale urban land subsidence, which is happening in some places at a rate of 30 centimeters a year. So what you see in this image is actually a groundwater extraction well installed level with the ground in 1938, but it's remained in place by soil friction, and the city has essentially sunk around it. So in this diagram, we see that over the course of the 20th century, the ground has actually been sinking much faster than children have been growing, meaning that if you were to actually mark your height on an extraction well, you would sort of never again be taller than the mark that you made on the pipe. And this is something that is a popular thing to do in Mexico City. So the rapid urban land subsidence in turn exacerbates urban flooding during the rainy season, as the topographic gradients required for urban drainage are first sort of negated and then reversed by the sinking. So Mexico City is plagued by both too much water and also not enough, with millions of people relying on deliveries of water by trucks to survive. For those of you who don't know anything about Mexico City, it used to look like this, right? A massive 2,000 square kilometer lake that used to surround the city and fill its sort of legendary waterways, was desiccated by Spanish colonizers and modern infrastructure projects, only to reappear again in the form of urban floods and what I would call the sort of toxic beauty of the Mezquital Valley. And this is the Endo sewage reservoir, which you saw on the map before. So if we recall the sort of essential conflict that the treatment plant introduced, let's sort of try to remember exactly what it was, right? So to recap, the government project to build the treatment plant introduced a conflict between farmers and the government's public health objectives. The farmers believed that the benefits of the wastewater's organic matter outweigh the risks of its contaminants, while the government believes the reverse. And so, the question we might ask ourselves here is, who's right? Whose idea of the soil and the soil's risks is more accurate, is more compelling? And what's sort of fascinating about this question to me is that, it's also a conflict that really cuts across the traditional lines drawn between victim and culprit in environmental justice struggles. Even if we see the Mezquital Valley as a sort of environmental disaster, the problem is not the usual one, where no one is willing to take responsibility for some kind of toxic aftermath. On the contrary, the environmental justice conflict here arose at precisely the moment when the government tried to take responsibility. The government's actually following the advice of the World Health Organization here, investing in wastewater treatment infrastructure. And I think it's fair to say that very few environmental justice conflicts begin this way, with global environmental standards being respected And yet one could ask, what do these global standards actually understand about the outline of the soil in the Mezquital Valley? In this soil, the outline of the pathogens are only one among many outlines we could see or that we could draw. Farmers in irrigation districts 3 and 100 would claim that there is much more in the soil to see than simply pathogens. And in this sense, the Mezquital finds itself in a crisis of representation, or more accurately, a crisis of representationalism. That's also a fundamental crisis in the structure of soil knowledge, I would claim. So what do I mean by a crisis of representation? To move through this sort of briefly, if we think about how the wastewater treatment plant sees the soil in the Mezquital Valley, or how the government would represent the soil, it looks essentially like this. This is what we might call the outline of the soil from their perspective. And in this table, we see the concentrations of the number of key protagonists in the wastewater that they've identified. We have the nitrogen, we have the phosphorus, which the farmers like, appearing in high concentrations before the treatment plant, and then in lower concentrations afterwards. And the same goes for lead, arsenic, cadmium, helminth eggs, which are the embryonic stage of the parasitic worm Ascaris lumbricoides. And of course, we have fecal coliforms. And if we look at these values and compare them to Mexican water quality standards, we can see that legally it is the biological part of this wastewater that fails public health tests, right? So the helminth eggs per liter and the fecal coliforms per liter are too high. And if we measure the wastewater after treatment, the great news is that all of the water quality standards are met. This is essentially the argument for the treatment plant, right? But what the farmers would argue is that this is a very partial view of the health risks that they face. We might say it's a very sort of selective outline. So for example, while the concentrations of heavy metals are reduced somewhat by the treatment process, they're not zero. And of course, as everyone here knows, heavy metals do not degrade in the soil. They are forever. They simply continue to accumulate. And if we take this accumulation into account, we see that in 100 years, both arsenic and cadmium levels in the soil will actually violate these same legal standards. And of course, we should remember that the heavy metals that were removed in the treatment process did not magically disappear. They've just simply been displaced into the concentrated sewage sludge that the treatment plant produces. The sludge is a kind of byproduct of the treatment process. And it also happens to be very high in nitrogen and other plant nutrients and is saved as a soil amendment to be sold back to the farmers as fertilizer. So using this sludge would effectively redistribute the heavy metals back onto farm fields, but this time in higher concentrations, shortening the timeline of agricultural inviability. And I just want to note here that concentration is sort of often synonymous with toxicity, right? Like if we notice that all of our contaminants in this table are measured per liter, concentration is the basic underlying logic of why wastewater is sent to the ocean in the first place. The idea is not to remediate the waste, but simply to dilute it. And the treatment sludge is a process of concentration. So even if it's going to a landfill, this has health implications for the people who live there. So what you can see then in this table is that the argument for which these strategies sort of more effectively protects public health depend on which outline of the soil are you looking at. Are you looking at the heavy metals or are you looking at the pathogens? And which water quality indicator are you looking at still tells you nothing about how they're actually managed in practice on the ground. So for example, flood irrigation actually produces more heavy metal concentrations at the entrance where the water enters the farm field during flood irrigation, further increasing the kind of contamination load. But also this 100-year time frame for when heavy metals exceed regulatory standards is also plant specific. So every plant has a sort of a different rate at which it takes up heavy metals. And in this case, the calculation was done for corn. But we could also ask, what about alfalfa? What about cilantro or soy? How many years left would we have with these plants? And what are the implications of growing them instead? Also, we might ask, how are these biological thresholds of safety determined? If the water has fecal coliforms, for example, how many times a day do you need to wash your hands, or with what techniques do you need to wash the vegetables to prevent transmission? Given a different set of management practices, could we get away with a higher threshold? But then also, if we were to make the decision to use a higher risk threshold, of course, the question becomes, who takes responsibility for that decision when someone gets sick? So this table teaches us anything about the Mezquital and about wastewater agriculture. What it teaches us is that no one can really afford to take the outline of the soil for granted. And again, what I mean by the outline is the beings, the entities, the living and non-living agents that we identify and trace in order to represent the soil. And in order to make sense of this conflict, I think we need to start mapping the vast and, I would say, as yet uncharted territory of material processes that contribute to the soil's formation in this system. So if we imagine that this was the sort of pre-wastewater agriculture soil profile in the Mezquital Valley, say, around maybe 1955, we might start to think of it not as a sort of pile of objects, as sand, silt, and clay, but as a soil defined by a certain set of soil-forming processes, each producing different effects in the soil. And some of these soil-forming processes would come from non-human agencies, like the smectite that you can see here. The smectite formed over the last million years and has a very high cation exchange capacity. It holds water really well. It's fertile, but it's also highly erodible under conditions of ecological collapse. We might also consider soil as a soil forming factor, the nitrogen fixing ants that support agave and other CAM photosynthesizers, creating ecological resource islands for sheep and for other organisms, also creating fiber for the production of ayate textiles, which are woven actually by using the barrel cactus that you see here in this image. You might also think of the sort of sacredness of the maguey itself as a soil forming factor that keeps the maguey plants in production, and whose roots are the main mechanical force keeping the fragile, arid soils from eroding during the torrential rainstorms that sweep through the valley every June. We might think about, for instance, the way in which this profile relates both human and non-human actors in the Mezquital in complex ways through soil properties. And in this sense, we would conceive of the soil itself as sort of emerging at the intersection of diverse human and non-human forces. And understanding this way, I think, would be enormously helpful to understanding really what changed with the introduction of wastewater agriculture when this soil was transformed into this one. Here we can see the same kind of smectite clay minerals that we saw before, but now their high CEC has become crucial for immobilizing heavy metals, keeping them from becoming bioavailable, an extremely fortuitous soil property for a wastewater agriculture system. We could also think about the surfactants, which are produced by industry that we saw before, causing the soil to kind of disaggregate and lose its structure. We might also think of antibiotics, which are not all the same with respect to soil. So sulfamethoxazole and ciprofloxacin are one of the most common antibiotics prescribed in Mexico City. And actually, Cipro has a half-life in this specific soil that's far shorter than sulfamethoxazole. Antibiotics that arrive in the wastewater sort of bind to clay surfaces and then remain active until they break down. And these sort of low-level concentrations make actually really excellent conditions for the evolution of antibiotic resistance. And today, it's actually quite easy to find bacteria in the soils of the Mezquital with multi-drug resistance. So genes that code for antibiotic resistance are also shared through horizontal gene transfer among and between distinct microbial species via plasmids, which are something that we also really need to understand in a wastewater soil. You see plasmids here as these kinds of DNA rings. And what's really astonishing about plasmids, especially in the context of the Mezquital, is that they contain genes that encode for resistance to both antibiotics and heavy metals. meaning that an increase in heavy metals in the soil causes an increase in antibiotic resistance and vice versa. So in this outline of the soil, we've sort of, in some way discovered a vast archive of genes sitting on clay surfaces as if they were sort of books in a lending library to be checked out. And the outline of Mexico's heavy metals, sort of born of its petrochemical industry, turns out to be physically inseparable from the outline of pharmaceutical medicine in this soil, whose plasmids make a single unified form out of modernity's two most defining features, oil and antibiotics. Increasingly worrying is also the high level of microplastics in the soil, which arrived to the Mezquital Valley mainly through the laundry of 22 million people, as well as the car tires that line its highways. We could also think about, for example, the E. coli and the pathogens and the Ascaris lumbricoides, the pathogenic amoeba, the enteric viruses, the Shigella, the Salmonella, that all also come in this particular wastewater as new arrivals to the profile, particularly the top layer of the profile, since those pathogens are confined to the first 5 centimeters in flood irrigation. But then again, we might also find the metformin as the most sort of devastating chemical conformation of the industrial diet in Mexico, where now we are actually irrigating corn with the diabetes medication that played a huge role in the NAFTA-based corn syrup, explosion of corn syrup-based beverages in Mexico, which actually produced the diabetes epidemic in the first place. So as you can see, we're kind of using a kind of a methodology of thinking through the soil in this way of trying to identify the sort of human and non-human agencies that make up the soil, mapping their relationship to historical and material processes in the city, and then using those agencies as a way to visualize and imagine the confluence of forces that the soil is sort of forming within and between in order to try to understand this region, because in fact, that's the only way that we can start to think clearly about the sort of contours of the environmental justice struggle in Mexico City. And of course, I think to think clearly about what it would mean to take care of our own shit, what it would mean to think about our bodies in connection to a soil in the agricultural hinterland of the city that we live in, and what that relationship would look like. For me, what's missing right now is that right now this whole conversation about the safety of wastewater agriculture is always really focused on the Mezquital Valley. And what's missing is really the other half of the story, where the agricultural products that the Mezquital Valley grows return to Mexico City as agricultural goods and produce. And in this way, they kind of participate in the production of the conditions of their own possibility. And I think should give Mexico City a real incentive to start thinking about how we could imagine a city that produced less pollution, how we could imagine a city that put less heavy metals into its waste stream. And at this moment, I think this kind of question is the moment in which we become capable of asking a larger question about wastewater agriculture. And this is what I would call the moment where we can kind of move from talking about wastewater agriculture to talking about wastewater urbanism. In effect, the whole idea of wastewater agriculture is sort of forgetting half of the system, which is the part that produces the qualities in an agricultural soil that are conducive or antithetical to life. The city is sort of always the other half of the wastewater pipe. And in this sense, we define wastewater urbanism as the forms of life that anticipate their consequences for the production of an agricultural soil. And these forms of life are sort of neither inherently rural nor inherently urban in the traditional sense of these terms. Wastewater agriculture sort of already made these categories irrelevant. In the case of the Mexico City Mezquital Valley system, the parameters of a wastewater urbanism coalesce around what I think are kind of the two fundamental questions that I'm going to show you here, conclude with here. And the first is, what would the city look like if it needed to produce a fertile agricultural soil from its waste? In other words, if this was the city's sort of main objective, what would have to change? And what would these changes look like? the urban design of Mexico City's streets, its markets, its sewers, its pharmacies, everything about its urban and industrial life leave a mark on the wastewater it sends to the Mezquital. And this all comes back to the city in the form of vegetables, dairy products, and meat. So the city has a profound stake in this question, but simultaneously, we also have to ask, what would the farm look like if it better anticipated its material connection to the bodies of 20 million people and the effluent of urban life? What kinds of agricultural practices, farming technologies, and health policies would be required to make wastewater agriculture safe? Because again, our central premise really in this project is that in a warming world, we really can't afford to let wastewater agriculture fail. Hope that was on time, and I look forward to your questions.